Alright, so next up in our material for Math 1410, we move on to, from lines in 3 dimensions, we're going to move on to planes in 3 dimensions. So we have a rough kind of intuitive idea of what a plane is, right? It's sort of a flat level surface. We're used to talking about, the coordinate planes, for example, right? So we're used to, in 3 dimensional space, if we draw our coordinate system out, right? We can sketch out the XY plane, this set of all the points where Z is equal to 0. We can sketch out the YZ plane where X is equal to 0. We can sketch out the XZ plane where y is equal to 0. We have these coordinate planes. And now, of course, I've only drawn the portions of those planes where all variables are positive, but you can extend these off into the negative directions as well. So if you want to generalize this idea of a coordinate plane, right, you want to take something that looks like one of the coordinate planes, but you want to change its orientation in space. You want a plane which is sitting there at some sort of angle, and we'll see that one of the ways to describe a plane is by simply taking, this sort of general linear equation that you would give for a line, or if I cover up the c times z, if I just kind of hide this part for a minute, ax plus by equals d. That's the equation of a line in 2 dimensions. Adding one more variable takes you to a plane in 3 dimensions. What's not clear yet is how do you actually kind of get an idea of what this object looks like. How is it oriented in space? What do these numbers a, b, c, d tell you about where and how that plane is located? One other way, just as 2 lines describe, or as 2 points describe a line, 3 points describe a plane. You can kind of imagine that if I have 3 points sitting there in space somehow, I can sort of connect the dots and construct that triangle. And that triangle's got to be sitting in some sort of plane, and so you can kind of think about extending this thing off in other directions to get an idea of what that plane looks like. Or if you had a pair of intersecting lines, right? If I have this line here meeting with that line there, those 2 lines are going to have a plane in common. This notion of span, this is something we might explore later on. This is the idea that a general point in a plane can be described in terms of vectors, in terms of a linear combination of vectors. And with lines, we saw that with a line, you need sort of one vector, one direction vector, and then every other point on the line is given in terms of that guy, some multiple of that vector. For plane, you need a second direction, so you need a second vector. But the main kind of key ingredient for most of our plane constructions is going to be this normal vector. And most problems where you have to figure out the equation of a plane boil down to figuring out how to obtain a normal vector to the plane. The normal vector is going to be, so the idea is that if you've got a plane, you've accounted for 2 of your 3 dimensions in space, there's going to be one direction which is left over that is perpendicular to every direction that lies in that plane. And that's where the normal vector comes into the picture. Okay, so here's one way to think about a plane. Let's close that bracket. So a plane is a 2-dimensional object, right? So let's kind of draw in our coordinate system. All right, so we've got our coordinate system, and we have some point P naught, okay, sitting out there in space somewhere. And I draw one vector v at that point. Well, once I've got that one vector, I can extend the line here, right? So I can now think about the line passing through the point P in the direction of that vector v, right? But if I just have a point in one vector, all I'm ever going to get is a line. I have no way of getting off of that line. So how do I get off the line? Well, the way I get off the line is I add a second vector. So if I add a second vector, let's say w, right? This allows me to get off the line. So what I have now is I have I can think about this. I have a second line which is passing through that point in the direction of a different vector. I can think of that pair of lines as giving me sort of a new coordinate system floating there somewhere in space. Now those lines aren't necessarily perpendicular, right? There's no requirement here that v and w have to be orthogonal vectors. Those lines might meet at some sharp angle, but as long as those two lines are not parallel, that second direction is all that I need. So you can sort of start to visualize the plane that you're dealing with here, right? So you've got this plane kind of hanging out in space like this. And if you wanted to get to some other point on the plane, let's say you're trying to get to this point over here, right? How do you get to that point? Well, you can think about drawing two lines to that point. You could draw one line which is parallel to W, or you could draw a line which is parallel to V, right? So basically, you introduce a grid system, right? You can introduce kind of a grid, one set of grid lines which is parallel to V, one set of grid lines which is parallel to W. They may not be rectangular grids; these might be parallelograms, but that's nonetheless good enough. So one way I could do this is I could say, well, I have what? I have this vector here, right, which is parallel to V. It's in the same direction as V, but I had to make it slightly longer. So I could say, well, that's going to be, it's some scalar multiple of V. So maybe I say that's S times V. It's some multiple of V. And then I have this guy here, right, which is the same as this vector here. This is one big parallelogram here. So that vector, well, that's parallel to W, but again, it's not necessarily the same length as W, so that's going to be some other multiple of W, say T times W. So now, how do I locate that general point in space? Well, I've got a couple of position vectors, right? I've got this vector here going from the origin to this point P naught. I've got this new point, let's call this guy P, maybe, I guess we're drawing that in green, P over here. And so I can draw the vector going from the origin to that point, like so, right? And I can play kind of the same game that we did with lines. If I call that R naught, and if I call this guy R, I could say, well, this R is given by, well, I go from the origin to this point P naught, so I add R naught. And then I travel in the direction of V for a little while, so I need to add on S times V. That gets me, so I go from here, now I'm here, I add S times V, now I'm over there. Right, I go here, there. And now I need to get the rest of the way to P. I need to travel this distance, and that means I need to add on T times W. So that's one way of kind of thinking about a plane is, you can describe a plane in terms of a pair of vectors. You need now two parameters, right? So you need two parameters, two vectors. So in this case, S and T, right? So you could think of this R if you want. You can kind of think of it as like a function of two different variables if you want, S and T. So this is one way that you can kind of, work things out, right? And you can, so if you're writing down kind of X, Y, and, so let's say, yes, you would get something that looks like this, right? So you would get something that looks like, X would be like X naught plus SV1 plus T W1, Y would be Y naught plus SV2 plus TW2, Z is equal to Z naught plus SV3 plus TW3. So you could think of a plane like that, and this is a useful way to think about a plane. This is, if you kind of continue on through the calculus sequence, this will eventually be useful to you if you make it as far as, let's say, calculus 4. I know most of you are not getting to calc 4, so this might not come in handy there. It may come in handy later on when if we get as far as talking about subspaces, vector subspaces, we might spend a little bit of time on that. Then this picture will really come in handy for us. But for doing sort of vector geometry in 3 dimensions, this point of view is not a particularly useful one, or at least so it's not a particularly efficient one. The way you want to kind of approach things in 3 dimensions is, rather than giving these two vectors which are parallel to the plane, you want to come up with one vector which is perpendicular. And so you say, you know what I want? I don't want v and w. I want, and let me get this point p naught out of the way. I want, the vector that I want is going to be, well, let's put it back. P naught is there. The vector I want is this guy. N, perpendicular to the plane. So N is perpendicular to both, I want something perpendicular to both V and W, and if it's perpendicular to both V and W, then it's going to be perpendicular to kind of any linear combination of V and W. So it's perpendicular to every vector in the plane. And if you've gone through the cross product videos, then you know actually what this n should be. N should be the cross product of v and w. So we'll see in the next video, when we do some of the examples, we'll see that this is kind of a key construction. This cross product construction to obtain the normal vector is a pretty standard trick when you're working with planes. All right. So here's an example. All right, and let's kind of do a quick sketch. This is an example where we want to work with this vector form on the previous slide. So I've got 3 points. I'm not gonna try to draw these accurately. Okay, P, Q, R. This will be a good warm up for things we want to do later. So I need 2 vectors that are parallel to the plane. This plane has to contain these 3 points. So these points are all in the plane. So if I draw a vector between a pair of points, let's say I draw the vector from P to Q, right? That vector has to lie in the plane because it passes between 2 points in the plane. Planes are these kind of flat objects. So if I kind of stretch a string between 2 points that lie in the plane, that string is gonna lie flat on the plane. So we can call that V, and let's just kind of take P as a common anchor. It's often convenient to anchor both of your vectors at the same point. We'll call the other one W. Well, then we know what to do here, right? We know that V is the vector PQ, so we do our head minus tail rule. We do 7 minus 2, 4 subtract minus 5, and minus 5 subtract minus 3, and we get the vector 5, 9, and minus 2 for V. Similarly, W, the vector from P to R, we get 0 subtract 2, 6 subtract minus 5, minus 2 subtract minus 3, and this gets us the vector minus 2, 11, and 1 for the vector W. So those are 2 vectors that are parallel to the plane, and so if we wanted to describe the plane one way, we could describe any other point on the plane. So any point on the plane would be given by, so one way to describe a point will be x, y, z equals, let's choose this point P as our reference, 2 minus 5 minus 3 plus s times 5, 9 minus 2 plus t times minus 2, 11, and 1 for some s and t. All right. But most of the time, like I said, we're not going to write down our plane in this form. We'll still want to be able to find those 2 vectors that are parallel, because once we have those 2 parallel vectors, we can compute their cross product to get a normal vector. All right. So the normal vector allows us to get a simpler equation, and here's how we do it. Okay. So the normal vector, we usually call the normal vector n for normal, is a vector with the property that it is orthogonal to every other vector that is parallel to the plane, right? So in this previous slide, right, the normal vector would have to be something which is parallel to, in particular, to both v and w, but also any other point that lies in the plane. Okay, so once you've got that normal vector, you can describe your plane, because what you do is, so you would kind of illustrate with a picture. So we put our coordinate axes in. Actually, let's not even bother with coordinate axes because that adds a lot of clutter. Let me just draw, so here's a plane. Okay, so we draw a plane like so. We fix our reference point, P naught, and let's say our normal vector is sitting here, okay? So the normal vector is perpendicular to the plane. So what does that mean to say that the normal vector is perpendicular to the plane? Well, if I choose any other point on the plane, wherever I decide to draw it, let's say here, okay? Here's my point P, right? Well, as soon as I draw a second point on the plane, then I can put the vector between them, right? Like so. That's going to be this guy. This is my vector, P naught P, right? That's a vector between 2 points in the plane, so it's parallel to the plane. And because it's parallel to the plane, by definition of the normal vector, it must be orthogonal to the normal vector. So I must have, so the consequence here is that we must have normal vector dotted with P naught P, right? Those two vectors have to be orthogonal, so that dot product has to be 0. So if we know that that normal vector has components, let's say A, B, C, then we can calculate the dot product. So remember, how does the dot product work? I should do A times the x coordinate here, so A times x minus x naught, then B times y minus y naught, and then C times z minus z naught. I add those up. That gives me the dot product. That dot product should be equal to 0. So I get A times x minus x naught plus B times y minus y naught plus C times z minus z naught equal to 0. Okay, so that gives me the scalar equation. You can also clean this up. You can write this as ax. So if you push the ABCs through the brackets, ax plus by plus cz. Now x, y, z, we think of those as variables. The x naught, y naught, z naught, think of those as fixed. So those are just numbers. So a times x naught is a number, b times y naught is a number, c times z naught is a number. If you combine all of those on the right-hand side, that's going to give you some other number, d. D happens to be equal to, if you want to write it out, D is ax naught plus b y naught plus c z naught. If you feel like including that, that's the value of D. Okay, so now once we've got this idea for the scalar equation, if somebody gives me a point and a normal vector, I can write down the equation for my plane, right? So the scalar equation is given by n dotted with, well, let's take this shorthand, right? R minus R naught is equal to 0, where as usual R here has been for us denoting this vector x, y, z. R naught is going to be the position vector for P naught, so 2 minus 3, 1. So if I subtract those two vectors, plug in the values, this gives me 5 minus 2, 3. That's my normal vector dotted with, so I do x minus 2, right? X minus 2 over here, and then y subtract minus 3 gives me y plus 3, z subtract 1, and that dot product should be equal to 0. Let's kind of separate that. All right, but we can go a bit beyond this. We can simplify, right? This gives me 5 times x minus 2 times y plus 3 times z minus 1 equals 0, and now we've got a sort of a single scalar equation. If you really want to, you can expand and simplify. 5x minus 2y plus 3z is equal to, what is it equal to? 5 times 2 is 10, plus 6 plus 3, so 5x minus 2y plus 3z equals 19 gives you the equation of your plane. All right, so that's it for this one. We'll look at some more complicated examples in the next video.